I got a question via email about example 13-4 on page 665. And the question is, why does this top end behave as a free end as far as going over this way or that way? First off, I want to point out that this rope doesn't pass, or the cable does not pass right through the beam. Rather, this piece is knotted on this side right here, and the far piece is knotted on the other side. It's tied off. And so if it tries to bend about the weak axis, so this top end of the beam, in other words, tries to go in this direction, tension quickly builds up in this cable, which prohibits it. And if the top end of the beam tends to go away from us, the tension builds up in this cable over here, which prohibits it from moving in that direction. So that's why, with respect to rotation about the weak axis, which would be an axis, well, I guess it's rotating down here, an axis like that, well, I can put it anywhere in the cross section. So if I put it up top, with respect to that cross section axis, this column acts like it's pin connected at the top. Now, the real question was about, how about this way? You know, you push it over that way, or it tends to go over that way as a result of the loading on the top. I think I'll put that in a different color. So you got P acting down on it. If it tends to go over that way, why doesn't the rope keep it from going over that way? And the idea, and same thing going in the opposite direction. And the idea is that the rope exerts a force which is away from the object where it touches the object along the length of the rope. So in the current position, the rope can exert no force in this direction, for instance, or in the opposite direction for that matter. Now, then it becomes displaced a little bit. You say, well, why, wouldn't it keep it from moving over then? And the way I see it, the author is considering the rope to be somewhat real. Like the stretch in the rope, if you try to pull it along, its length is negligible. But if, let's say, you've pushed it to the side a little bit, we'll view it from the top. I think I'll try to draw it more the way it is. So somebody has pushed that top end a little bit to that side, so the rope is exerting a force on the beam that's in this direction. And the deal is, even with a huge tension having built up in the rope or in the cable, and if the cable was really quite taut to start with, very taut to start with, so that we already had a pretty good sized tension in it, you push it over to one side, and a huge tension starts to build up as in response to a relatively small force. Because if we look at either one of these, draw the vector component diagram, we have whatever its total force, whatever the total tension in there is, the total force associated with tension, it'll have a component that's along the original direction of the rope, and one that's perpendicular to the original direction of the rope, and those two components will add up to the total tension force. But this one, even for even when the tension force is huge, this is going to be a tiny little force. So the rope, maybe I should have, it is going to exert about a tiny force restoring it if this top starts moving out of position, not enough to keep it, maintain it as if it were pinned in that position. And again, with this whole buckling criterion, we're using the small angle approximation. So we're talking about a very, a small displacement of the top. I know we tend to, draw the picture. Okay, when it deflects for this one, the slope is going to be vertical at the top, and then we tend to draw it so that we can see the kind of shape that it takes on, as if this was a big displacement over here, but this is supposed to be a tiny little displacement. Okay, so once again, why did they treat it as pin connected for motion of the top in that direction or that direction? Because it puts the rope directly in tension. In other words, we're moving the top end away from the rope in the exact opposite direction to the direction that the tension of the rope is going to pull it. And then sideways, why do we treat it as if it's free? And it's essentially the rope offers almost no resistance to motion of the object in this direction. The other thing, another thing about that, when you move it over, say, a centimeter, if you try to move it this way, 1 centimeter, to move it a centimeter in this direction, you would have to stretch the rope a centimeter. To move it a centimeter in a direction perpendicular to the rope, you'd hardly be changing the length of the rope at all. It'd be a tiny change in the length of the rope. Whatever if that's a centimeter, it'd be the length of the rope is going to change by whatever it was. And if the rope is a meter, 100 centimeters plus 1 centimeter squared will be the new length of the rope. So if you moved it over a centimeter, the new length of the rope would be, I'm going to go ahead and do that on my calculator. New length of the rope would be 100.005 centimeters. In other words, it's essentially the same length as what it was before you pushed it over a centimeter. So it doesn't stretch the rope enough. The rope's not pulling in the right direction to fight that, and so the author in that example treats it as a free end if the displacement is this way or that way, and as a pin connection at the top, if it's that way or that way, the rope certainly isn't going to do anything to prevent the angle that the beam makes, prohibit it from changing like the fixed connection does at the bottom. So the top end for rotation about the strong axis, the one along the rope, is going to act like a free end.